everyone and welcome to the final video in our three-phase circuits course. In this video, we are going through a comprehensive quiz designed to test your understanding for what we covered in this course. If you watched all the 12 videos in this course, this quiz is a great way to check how well you have mastered the material. And if you have not completed all the lessons or videos, don't worry, this quiz will help you to identify your weak points and guide your learning moving forward. Let's start. The quiz structure. The quiz consists of 10 questions. The questions format include multiple choice, calculated numeric, multiple answer, and true and false. Each question is timed and weighted based on its difficulty, with the total marks for this quiz is 50 marks. After you finish the quiz, you are going to find detailed answers and feedback. I'm going to direct you are going to find the answers within the videos. Please complete the self-assessment and share your score in the comments. Before you start the quiz, you need this answer sheet. That one is 10 questions. So that one includes the type of the questions and the time for each question. And then you are going to add your selection here. And for questions 7 to 10, you are going to add your answer. So either take an image for that one or copy that one to your notes. During the quiz, you need a stopwatch. You are going to stop the video. You are going to run the stopwatch based on the question or the allocated time for each question. And then you are going to resume to go to the next question. The quiz will start after 5 seconds. Answer the following questions. Question number 1. For a single-phase circuit, the cross-sectional area of the return wire is equal, double, half, quarter to the cross-sectional area of the go wire. The time of this question is 30 seconds. Question number 2. A three-phase system delivers constant, instantaneous electrical power to the load. Agree or disagree? The time of this question is 20 seconds. Question number 3. In the three-phase system and star connection, the following properties are held. The line voltage leads the phase voltage by 30 degrees. The line voltage lags the phase voltage by 30 degrees. The line voltage equals root 3 the phase voltage. The line voltage equals the phase voltage. The line current equals the phase current. The line current equals root 3 the phase current. Please note, this is a multiple answer question. The time of this question is 60 seconds. Question number 4. A balanced star-connected load has an impedance of Z equals 20 angle 60 degrees ohm per phase. The phase RMS voltage is 220 volt angle 0 degrees. The phase C current in ampere is. Choose one answer. So the time for this question is 60 seconds. Question number 5. The delta connected load shown in the figure has a load impedance Z equals 10 angle minus 40 degrees ohm per phase. The RMS voltage is 300 volt angle 0 degrees. Calculate the line current of phase B in ampere. Choose one answer. So the time for this question is 60 seconds. Question number 6. A balanced three-phase system star-connected has a phase RMS voltage of 230 volt and a phase RMS current of 18 ampere. The power factor angle is 60 degrees. The reactive power in kilovar units is. Choose one answer. The time for this question is 60 seconds. Question number 7. Three-phase source feeding different loads. Load number 1 takes 20 kilowatt with 0.8 lagging power factor. Load number 2 takes 12 kilowatt with 0.6 leading power factor. So we need to calculate the source apparent power. Please note that one is calculated numeric question, so you are going to do analysis in your notes. The time for this question is 150 seconds. Question number 8. The power triangle of a balanced three-phase system has an active power, real power, of 45 kilowatt and a reactive power of 45 kilovar. A delta connected capacitor bank is installed to improve the overall power factor of the system, providing 40 kilovar of the capacitive reactive power. So we need to calculate the new apparent power in kilovolt ampere and the new power factor of the system after the capacitor bank is connected. That one is calculated numeric question. The time for this question is 120 seconds. Question number 9. A delta balanced connected load has an impedance of 12 plus J16 ohm per phase and fed from unbalanced supply voltage where VAB equals 220 angle 20 degrees, VBC equals 150 angle minus 140 degrees, and VCA equals 220 angle 60 degrees. So we need to calculate the phase A line current in ampere. That one is calculated numeric question. The time for this question is 180 seconds. Question number 10. A balanced star load of 8 plus J6 ohm per phase is fed from unbalanced supply voltage where VA equals 220 angle 0, VB equals 180 angle minus 90 degrees, and VC equals 180 angle 60 degrees. We need to calculate the positive, negative, and zero sequence currents. That one is calculated numeric question. And the time for this question is 300 seconds or 5 minutes. That quiz is finished. Model answers. Question number 1. For single-phase circuit, the cross-sectional area of the return wire is equal to the cross-sectional area of the go wire. So you can visit the video Why Three-Phase Systems Outperform Single-Phase with MATLAB and SIMULINK. Question number 2. Three-phase system delivers constant instantaneous electrical power to the load. Definitely agree. We proved that one mathematically. So you can visit the video Three-Phase course, Three-Phase Power. Question number 3. In the three-phase system and star connection, the following properties are held. Line voltage leads the phase voltage by 30 degrees. The line voltage equals root 3 the phase voltage, and the line current equals the phase current. So you can visit the videos Three-phase circuit star and delta sources or three-phase star load analysis with MATLAB Simulink examples. Question number 4. A balanced star-connected load has an impedance of Z equals 20 angle 60 degrees ohm per phase. The phase RMS voltage is 220 angle 0 volt. We need to calculate the phase C current. Either we are going to calculate phase C current IC equals VC over Z, and VC will be 220 angle 120 degrees over Z 20 angle 60 degrees. So that one will be 11 angle 60 degrees. Ampere. Or you calculate phase A current, which is 220 angle 0 over the impedance 20 angle 60 degrees, and that one will be 11 angle minus 60 degrees, but IC will be shifted 120 degrees from that one, so it will be 11 minus 60 plus 120, that one will be 11 angle 60 degrees. Question number 5. The delta connected load shown in the figure has a load impedance Z equals 10 angle minus 40 degrees ohm per phase. The RMS voltage is 300 volt angle 0. We need to calculate the line current of phase B. So we are going to calculate phase current for phase B, which is VBC over Z. That one will be 300 angle minus 120 over Z, which is 10 minus 40. So that one will be 30 ampere angle minus 80 degrees. So the line current for phase B will be 30 root 3 angle minus 80 minus 30. So that one will be roughly 52 angle minus 110 degrees ampere. So the choice is B. Question number 6. A balanced star-connected three-phase system has a phase RMS voltage of 230 volt and a phase RMS current of 18 ampere. The power factor angle is 60 degrees. The reactive power in kilovar units is, so Q equals 3V phase, I phase, sine phi. So that one will be 3 multiplied by 230 multiplied by 18 multiplied by sine 60. And that one gives you 10.76 kilovar. Please note, choices A and B are totally wrong because the reactive power has no angle. Question number 7. Three-phase source feeding different loads. Load number 1 takes 20 kilowatt with 0.8 lagging power factor. Load 2 takes 12 kilowatt with 0.6 leading power factor. We need to calculate the source apparent power. What we are going to do, we have two loads here, load number 1 and load number 2. So we have P1 and P2. So we need to calculate Q1 and Q2. Then the total power from the source, P total, will be P1 plus P2. And the total reactive power will be Q1 plus Q2. Then we can calculate the apparent power of the source. So for load number 1, we have the power factor 0.8. So the angle is 36.8. So tan phi 1 equals 0.75. So we can calculate Q1 equals P1 tan phi 1, which is 15 kilovar, positive. Regarding load 2, phi 2 equals cosine inverse 0.6, 53.13. So tan phi 2 equals 1.33 or 4 over 3. So Q2 equals P tan phi 2 minus 16 kilovar. So why is minus? Because that one is leading power factor. So P total equals 32 kilowatts, Q total equals minus 1 kilovar, so S total equals root P total square plus Q total square, which is 32.02 kilovolt ampere. Question number 8. The power triangle of a balanced three-phase system has an active power of 45 kilowatts and a reactive power of 45 kilovar. A delta-connected capacitor bank is installed to improve the overall power factor of the system, providing 40 kilovar of capacitive reactive power. We need to calculate the new apparent power in kilovolt ampere and the new power factor of the system after adding the capacitor. So we have the power triangle as we can see here. P equals 45, Q equals 45. So the S total now is 45 root 2 and the angle is 45 degrees. We're going to add a capacitive load with 40 kilovar. So this means that we are going to drop that one by 40. So the new Q is 5 kilovolt ampere reactive. So that one is positive 5. And we have the power P is 45, so we can calculate S in U, which is root P square plus Q square. So let's look here. So S equals root 45 square plus 5 square. That one is 45.28 kilovolt ampere. What about the new power factor? So the new power factor will be tan inverse Q nu over P. So that one will be tan inverse 5 over 45, gives you 6.34 degrees. And the new power factor is cosine this angle, which is 0.994 lagging power factor. Question number 9. A delta balanced connected load has an impedance of 12 plus J16 ohm per phase and fed from unbalanced supply voltage where VAB equals 220 angle 20 degrees, VBC equals 150 angle minus 140, and VCA equals 220 angle 60 degrees. We need to calculate the line current of the phase A. So we have the delta connection here. So here we have IA, phase current of phase A, and that one is IC. So if we like to calculate this current, which is a line current here, we are going to use Kirchhoff current law, where I equals IA minus IC. But we can do it simple rather than that one. We have IA multiplied by root 3 and shift by 30 degrees. That one, if the system is balanced, the system is unbalanced. So we need to calculate IA and IC. So Z equals in polar form 20 angle 53.13. So IA equals VAB over Z. So IA equals 11 angle minus 33.13. And in the rectangular form will be 9.21 minus J6. We're going to calculate IC as well, VCA over Z. So IC in the polar and rectangular form as shown here. So we can calculate IA, which is IA minus IC, equals 7.52 angle minus 103.15. Question number 10. A balanced star load of 8 plus J6 ohm per phase is fed from unbalanced supply voltage. VA equals 220 angle 0, VB 180 angle minus 90, and VCA equals 180 angle 60 degrees. We need to calculate the positive, negative, and zero sequence currents. So we are going to solve this problem. We have two scenarios here. Scenario number 1, we are going to calculate the positive, negative, zero sequence of the voltage using this matrix. So we have the values here. Then we are going to have positive sequence for the current, V positive over Z. Negative sequence, V negative over Z. And zero sequence, V zero over Z. Or you are going to calculate from phase voltages the phase currents, where IA equals VA over Z, IB equals VB over Z, IC equals VC over Z. And you are going to use the same matrix here to calculate the positive, negative, and zero sequence of the currents. Should give you the same answer. I hope you enjoyed the course and thank you for watching. See you in the next course.